patterns. Why is that advantageous? Yeah.
Motion. And
Motion.
also you can be easily with a blind spot and like stuff like that. Like,
Yeah.
Wait, what?
Yeah, our brain likes to.
That's
Yeah.
how
What?
we interpret.
Yeah. So our brain likes to make patterns, maybe because there actually are some patterns out there that are kind of important, like things fall and stuff, right?
And
When you
then
drop
we
them.
wouldn't see motion if we didn't make patterns.
Yeah. So okay. So I'll ask the question again. Why have we settled upon this particular bunch of like 15 functions that we seem to just be dwelling on over and over again?
I don't know.
Because I made you. Yeah, I know. So now's the time to grow up and think about the real world. Like, why is it like a Kendall?
How they represent real life?
Yeah, because they represent real life. Give me an example, specifically. Like give me, like throwing things and parabolas. Yeah. Damn it, that's why. That's why we care about parabolas. We care about parabolas because they model real world phenomena.
But I don't throw anything.
You don't throw anything? You don't play any sports? You don't throw anything ever?
You should model it something like that.
Yeah, that's why and there's like time, exactly. Thank you. Now we're having real talk. We care about things like parabolas because there are real world phenomena out there which we care about, which behave parabolically, like things in free fall. We care about sine functions because there are things in the real world which behave sinusoidally, like tides and whatever. Okay, so for every function that's out there why do we care about exponential growth?
Population.
Yeah, because that's what happens if you leave your cheese out on the counter for like a couple months, right? What? Why do we care about hyperbolas? Because that's what happens if you there are examples.
No, we don't.
No, there are tons of examples of hyperbolic
line.
motion.
Conics in this room.
When a thing goes towards another thing is pushed away.
There's millions of examples, but like things. There are a lot of things which move around the sun in a hyperbolic fashion, right? If the escape velocity is such that if like a comet, right, normal comets move in ellipses, but if it gets too close to the sun, it'll just gone forever. You'll never see it again. All right. Point is, for every function, it exists, and it has attracted our attention over time, and it's in like the inside cover of your calculus textbook because it's a function which, for whatever reason, we have come up with to explain phenomena in science that we care about. Okay, so the real answer to why we have the particular group of functions that we have and not some other group is because science, right? That's like sort of the short answer. Okay, so why do we care about continuous functions?
Real life stuff doesn't jump.
Yeah, because real life is continuous, maybe. Okay, and certainly.
You never know.
Okay, so at least in the pre 1910, I could very confidently state that the universe just appears to be continuous. Things appear to move in a continuous manner. The quantum physics, which no one really understands anyway, seems to cast some doubt on that. But at least at some kind of macroscopic level, at least the Newtonian universe seems to be continuous, okay? So one answer is we care about continuous functions because we're using math to model physical phenomena. Physical phenomena appear to just be continuous. Another answer is the answer that someone gave like 10 minutes ago. I think it was Sydney, I can't remember. That basically the continuous functions are the only things that we can really say anything about. See, but it's like discontinuous functions are so ridiculous. There's no possible way to. Maybe you said that. That's right. There's no possible way for me to say anything about them, right? They're just so grotesque, and there's so many possible different ways in which they could just be doing anything whatsoever. All right, this is a long-winded ramble, but basically, my point here is what you're going to find. I mentioned last class that continuity is like this fundamental idea that's going to come up again and again in calculus. That's because continuous functions are about the only kinds of functions which we can even say anything about. If a function's discontinuous, all bets are off. You will find that in almost every single theorem for the rest of the year, we'll start with, if the function is continuous, then blah, 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 blah. We need continuity in order for us to be even to make any sense of what's going on. All right, Eric, here we go. An example. A classic example of a theorem which requires continuity. And, conveniently, it's a theorem that you have already heard about. It is called the intermediate value theorem.
Yeah, that's all. Never heard of it.
What is the intermediate value theorem? Do you remember? Uses.
The one that says if a function is negative at one point and positive at next point and it's continuous, then there's a 0 point between them.
Yes, we saw this last semester when we were searching for roots of polynomials. Buses says if you have a function which is continuous, like a polynomial, and it's negative somewhere, and it's positive somewhere else, then it must somewhere be 0, right? The actual intermediate value theorem, which I mentioned in at least one of the classes, I think not all of them, says not just that it must be 0 somewhere, but in fact that it must be any intermediate value between the values of the function at a and b. So if you give me any function whatsoever, which is continuous, and let's say without loss of generality that f of a is less than f of b. So we have some kind of picture like this. So the function starts at value f of a and ends at value f of b. Well then, if you pick any y value whatsoever between f of a and f of b, then you finish the sentence. What is between a and b? The x value such that, call this number k. Yeah. Somewhere you have to cross this line, right? If this function is continuous, then somewhere you have to cross this line. So the intermediate value theorem just simply says, okay, ready? If f is continuous on the open interval AB, or the closed interval AB, in other words, it's well behaved on an entire closed interval, then there exists a C on that interval AB such that, oh wait, I forgot a sentence. If f, oh, bless you. If f is continuous on the interval AB and we have to pick a value, k, which lies somewhere between f of a and f of b. So k is some intermediate value between these two values. Then there exists a point C on the interval AB such that f of c is k. Cool? I think it's cool.
Is interval open or closed?
I guess it should be closed. I don't know. Maybe I want to make it like maybe I want to do that. Yeah, let's do that. Okay, so in other words, if I want to, I just change those to be k being actually in between f of a and f of b as opposed to equal to reason. So this is kind of like, so it's like here you are, right? So it's like you're here now, and later you're here, and this is like some annoying task that you don't feel like doing. So maybe you have to, I don't know, like you have to like write some English essay or something. It's only like 1 page long. You should just get it over and be like, I don't feel like it. But by the end of the night, before you go to sleep, you have to have like done this. So it's kind of like you can procrastinate. You can, I don't want to do it. Okay, but then eventually you have to do it.
What have you done? You undo it, you undo the essay.
No, you lost it. You lost it. Yeah, you got the dog, and then you had to like do it again. Power out, you had to do it again. Okay.
You just have to do it like 8 a.m. in the morning. Can't you just do it after you wake up?
Yeah.
I know.
Good.
People do their homework in the morning and have like, some serious.
Good. So, by the way, this says that there exists a point C. It doesn't say that there's exactly one, because of course the function could have value k at multiple points. All right. Running out of time. Oh no, not running out of time. All right. So what is? No, we actually are kind of running out of time. What is? So what is the proof of this?
This is like not a question.
Proof?
No, can we not?
50
Yeah,
minutes.
good. We cannot. Yeah. The answer to proving this is no. All right. The proof of this is really, really, really hard. And that is because, you might say, that this theorem is just so obviously true. And you may have noticed in math that there's like an inverse relationship between things that are very, very obvious are actually quite difficult to prove because they involve very low-level concepts and things.
And there are not that many, like,
There's not much to work with.
Yeah.
Yes. Okay, so this is in almost all calculus textbooks like ours. This proof is skipped. If you take a serious fancy math class in college, they will prove this. But this proof depends on certain advanced properties of the real numbers, which are typically not taught at a high school level. But Arun, we learn them in logic math, so we will do a proof of the intermediate value theorem in logic math.
And it takes like 40. It
It's
takes
not
like 45
that hard,
minutes.
right? Yeah.
It takes so
well,
long.
but as long as it's really slow and stuff. But the actual proof is like a page.
Yeah, it's actually not that long.
So no. But even though we're not going to do the proof, we should appreciate. We should appreciate why every point, okay. So if you're a serious person and you learn some calculus theorem, you should just begin to like think critically about what's going on. You might say, for example, why is continuity necessary? Why do we insist on continuity? Yes, Calvin.
Because you could just skip at K and say, nope, we're gonna go somewhere else completely. So like, if you're going up towards K and then you just skip past it.
Yeah, that is correct. Calvin says that if you give me some K value between f of A and f of B, if I do not insist that the function be continuous, then I could easily just jump over it, right? I could just kind of go, well, this is, I don't know what that is. That's like, yeah, this is like you fast forward in time and then you hope that your normal self like wrote your English essay, so you don't have to experience it. What? Plagiarism, yeah. Also, in addition to insisting on continuity, why do we insist upon continuity on the closed interval? Which we seem to spend all this time wasted-ish talking about this formal definition of continuity on a closed interval. Why must that be true? If this is A and this is B and the function looks like this and you give me some K value in between, why do I have to be, yeah, Rohan?
The whole function except for f of A could be over K and f of A could be below K.
Yup. Rohan's imagining this situation, that the function looks something like that, right? This function would be continuous on almost the entire interval, but not continuous on the closed interval. And so I can't make that guarantee. Follow?
Yes.
Okay, so that's continuity. I was going to do like an example, but let's skip that. Because we're going to have a quiz. Let's have a quiz.
Oh my gosh.
Yes.
Actually, can we do the example? Yeah, let's do it.
All right. Clear your desk. Put all your stuff away. Those of you at home, make yourself a quiz.
What? I wish I was you right now.
Make yourself a quiz. Mail it to me with a check, and I will grade it and mail it back to you. So I think we're done for today. You can turn that off. Bye. That is the end of lecture 5. Goodbye.
You could just put